Hi, everyone. Welcome to lecture 21. And so today we're going to talk about matrix multiplication and, the exponent of linear algebra and how fundamental matrix multiplication is for linear algebra, computationally speaking. Okay. And along the way, we're going to see a different model of computation today, which is mostly algebraic in nature, right? So we're just going to use algorithms that only use algebraic operations like additions, multiplications, division, and multiplication, or subtraction, sorry. All right. So, okay. There's going to be some advanced trivia, and then we're going to talk a little bit about some matrix multiplication. And then we're going to talk about how we can relate this exponent to other problems which are fundamental linear algebra. And then we're going to one of them being matrix inversion. So we're going to see how matrix inverse and matrix multiplication are computationally the same. And then we're also going to discuss a little bit the determinant, okay, and try to relate the determinant, computing the determinant of the matrix to the matrix multiplication exponent. Okay, and if there is some time in the end, I will show you how you can, compute partial derivatives really quickly, which is also probably known to you if if you heard this in machine learning as the backpropagation algorithm, right? So this algorithm was independently discovered by algebraists and by people doing machine learning or people doing in other areas as well. So it's a very famous algorithm, and as it is very important, was discovered many times independently. Okay, so all right, so until 5 minutes before lecture started, I was going to give you guys some time today to fill out the evaluation. Please evaluate the course. I really read the feedback, or if you just want to give me feedback one-on-one as well, I'm happy to just listen to you guys, what you found about the course, what do you think should change, or what do you think should improve, and what do you think worked great. But right now, it looks like you cannot access the web page until tomorrow. So I will give you time on Thursday or next week, depending on how the deadlines go. Okay, so then, but if you have a chance of doing this, please rate the course. That'd be great. And I'm new to teaching, so this course is also a learning experience for me. All right. And another thing is the end of the term is approaching. So, if you want to think about the next steps, we'll be discussing the next steps in the next lectures as well. And I highly encourage you to consider taking more advanced courses next term. So for example, we offer lots of graduate courses, which some of them will take some of the subject further or explore different areas of algorithms. And there's pretty cool courses next term. So I highly encourage you to go there and look on the webpage. CNO also has a lot of graduate courses, which are a lot of fun, and math. So just, if you're thinking of taking another course, by all means, or, you should try out some of the research opportunities at University of Waterloo, and you can just Google them. Next lecture or the lecture after, I will give you guys the more precise links, but you can look for URAs or URFs or USRA. These are all research opportunities at the university, and now that you have a lot of, mathematical maturity, you should definitely try to do a little bit of that before you graduate. Okay. So, all right. So then let's cut to the chase here. Right. So now let's talk about matrix multiplication. So matrix multiplication of the problem is very easy to state, right? So my input here is I have two matrices A and B, and I want to compute the product of these two matrices, right? And let's just say that those two matrices are square for now. Okay, let's not deal with rectangular matrices for now. So if you think about it, if I take a matrix, A1, 1, A1, 2, A2, 1, A2, 2, then I multiply by a matrix B1, 1, B1, 2, B2, 1, B2, 2, what I want to compute is this matrix C11, C12, C21, C22, right? And so, and now what is this matrix, right? Well, this matrix is the product of those two. So for example, we would have that C11 is equal to A11, B11 plus A12, B21, and so on, right? So this is the usual way that you know how to compute the product of matrices. All right, so, and this is the naive algorithm that we just talked about, right? So this naive algorithm just computes n matrix vector multiplications, because if you think about a matrix A, and then I can think of the matrix B as a bunch of rows, like vectors, like B1, B2, up to Bn. And then I could, the computation that I described is essentially just kind of, you know, multiplying A by B1. It's just that I did row by row, right? But essentially it's the same as computing A times B1 and then A times B2 and so on, right? So we're computing n matrix vector multiplications. And how long does this algorithm take? Well, the running time of this algorithm is O of n cubed, right? Because each matrix vector multiplication takes O of n squared, because I have to at least read all the entries of A. Does that make sense? So it just takes linear time in A. So the running time here is O of n cubed, right? And the question is, well, as always, right? Can we do better, right? And how much, like, what is the limit of better here before we even answer this question, right? So what is the limit of better? Well, we know that it has to be omega of n squared, because I have to read the entire input, right? So I have to read input, which has size 2n squared, right? Like, and I'm assuming here that, you know, let's say that the elements of the field F, so F here is a field. Okay, let's say that the elements of the field F just take like O of 1 to read and write and so on. Okay, so we're kind of in the word RAM model, sort of. Okay, like word RAM model. Okay, so then what is the limit of better here? The better, it has to be like omega n squared, right? Just because you have to read the input, right? But then, you know, apart from omega of n squared, you know, all bets are on, right? So, and the answer is, and which was very surprising, it came in 1969, that the answer is yes, we can actually do better than n cubed. And this is due to Strassen. And the idea here is that we divide the matrix into blocks and we reduce the number of multiplications needed. Okay, so, and the idea is that addition, okay, addition is very cheap. So what you should think is addition is very cheap. And multiplication is expensive. Okay, so what we want to try to minimize is to minimize the number of multiplications, right? So we want to minimize number of multiplications. Okay, so all right. So how do we reduce the number of multiplications, right? So here's the idea for Strassen's algorithm, right? So suppose that n is a power of 2, just for simplicity, right? We can always do that like by increasing the matrix by at most 2, right? So so let's say that, you know, we have these square matrices like A, B, and C, such that C is equal to A times B. Now, if we divide these matrices into blocks of size n over 2, right? So the matrix A will become like a block matrix, right? So here we have the blocks. Like we're just dividing the matrix A, the matrix B, and the matrix C in blocks of size n over 2. And the thing is, if you did the naive algorithm here for Strassen's algorithm, right, you can see that we're still going to use 8 multiplications, right? So like if I look at C11 as like A11, B11 plus A12, B21, C1 equal to A11, B12 plus A12, B22, and then C21 is equal to A21, B12 plus A22, B22, and C22 will be equal to A21. Oh, sorry, this is 21 should be B11 and B21. And this is B12 plus A22, B22. Now, if we did this naively, right, like just as we did here, well, how many multiplications do we have? Well, let's count. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 distinct multiplications, right? So you can see that all of these multiplications are distinct. And now what we would have the following induction, right? Like the number of multiplications that we need for n by n matrices is less than or equal than 8 times the number of 8 multiplications of n over 2 by n over 2 matrices, right? Plus some constant times n squared, because we're just saying adding 2 matrices takes like O of n squared, right? Because I can just look at entry by entry and just add the entries, right? So that's cheap. But if you look at this recurrence, it will just give you that mn is equal to O of n cubed, right? So somehow we need to do something different, right? So here is Strassen's insightful idea, okay? Or like, can we use less than 8 multiplications, like strictly less? Okay. And the answer is yes. And then he found those multiplications, and we're going to look at it now, right? And by the way, this idea, was inspired. Okay, so this idea was inspired by another algorithm, which is known as Karatsuba's algorithm. For polynomial multiplication. Okay, so that's a different polynomial multiplication. So, Strassen already knew that like to multiply 2 polynomials, you can do it in a way, you can do a divide and conquer like this, and you do save on the number of multiplications. And he just asked, okay, does the same work for matrices, right? And as we're going to see, like this is a little bit more involved than Karatsuba's algorithm, right? So here's what Strassen did, right? So you can just define the following matrices. We're going to have S1 is equal to A21 plus A22. S2 is equal to S1 minus A11. S3 is equal to A11 minus A21. And S4 is equal to A12 minus S2. Okay, so you define these matrices. And you also define like T1, T2, T3, T4 like this. It's pretty kind of non-intuitive, right? So you just define them like that. And the idea is that now what we're going to do is we're going to compute 7 products. Okay, so we're going just to compute the products. P1 is just going to be A11 times B11. P2 is going to be A21 times A12 times B21. P3 is equal to S4 times B22. P4 is A22 times T4, and so on. So you compute these 7 products, okay, using either entries of like the subblocks of the matrices or the new matrices that you constructed, okay? And note that all of these are like n over 2 by n over 2, right? So same as these, right? So all of these are n over 2 by n over 2. Okay. And then once you do this, what happens is, so we have these new matrices, we have these products, and now let's see how we can compute just with these 7 products. Okay, just with these 7 products, let's see how we can compute like the product C, right? So to do that, always see first as well. Note that for C11, that's pretty easy because we have A11, B11, we're computing as P1, and we have A12 times B21, so that's P2. That's easy, right? Now let's see how we compute like C12. Well, C12 is A11 times B12 plus A12 times B22, right? Now, how do we compute this, right? So, okay, so let's look at the entries that have like A11. Let's look at the entry at the products that have A11, B12, A12, and B22, and let's see if we can combine them, right? So certainly P1 can be involved. P2 could be involved because it has A21, right? So P3 can be involved. P4, well, doesn't need to be involved right now because it doesn't have like any of the elements from here. And then P5, if you remember, P5 has A21 plus A22, right? And T1 has B12 minus B11. So T1 has an element from the product that appears here, and P6 is S2 and T2, which well has A11 and has B22, right? So we have those matrices here. So I have P1, P2, P3, P5, P6. Okay, but now once you compute it, you can just see that it will be equal to P1 plus P3 plus P5 plus P6, right? So how do we do this? Well, let's just open it up. A11, B11 plus now P3. What is S4? S4 is A12 minus S2 times B22. And then we have P5 is equal to S1 times T1. But what is S1? S1 is equal to A21 plus A22. Okay, minus, sorry, P5 is S1, yeah, times T1, and T1 is B12 minus B11. And then we have P6, which is S2 times T2. But what is T2? T2 is equal to B22 minus T1, right? And now if we just collect the terms that we want, right, we need to see that the rest cancel. All right, so what are the terms that we want here? Where do they appear? Well, they certainly appear in, oh, okay, that's a little, I picked the worst one to compute. Let me just do it again here, 1 second. Okay, so let's just open this up. Let's open it up a bit more. So let me just do it here because the thing is A12 is appearing here, which means that like, well, A12 has this coefficient here, right? So we better open up everything. So we have, so P3 is S4 times B22. So we have A12 and S4 is minus S2. And so this is plus A11 minus S1 minus A21 minus A22. And this is times B22. Plus P5 is S1, which is A21 plus A22 times T1, which is B12 minus B11. And then we have P6. And P6 is S2, which is A21 plus A22 times P6, oh, sorry, is S2 times T2. Yeah, T2 is B22 minus B12 plus B11. Right? All right. So now we have the terms that we would like. So let's just circle that term that we like. well, we like A12 times B22. So this term is right here. So I'm just going to circle this guy. And then the other one is A11 times B12, right? So did I compute it correctly? A11 times B12. Let me see. A11. Oh, yeah. So we have A11 is here. And then we have B22. 1 second. Do I have it wrong here? B3. So A12. And then we have, I think. So this is A11 times B12. It's not showing up here. Sorry, let me see if I did something wrong. So P5 is S1, A21. Oh, sorry, yes. I did it wrong here because, so I think, yeah, I think there's a mistake here. Let me correct this one. S1. So wait, S2, P6 is S2, T2. So P6 is, oh, sorry, yeah, it's right here. The mistake is right here. So P6 has an extra term here. So I did S1, my bad. Yeah, so P6 is S2, T2, and S2 is S1 minus A11, right? And then I also have here that A11 times B12 is showing up here, right? So all we need to show is all the other terms cancel, right? And it's appearing with the proper sign. Okay, so now let's do the cancellations in blue, in green here, right? So A11 times B11 gets canceled with this A11 times B11 here, right? So this is the first cancellation. And then we have A11 times B22 cancels with this A11 times B22. So this cancellation also happens, and this guy is completely eliminated. Now, if I multiply, note that here I actually have minus A21 minus A22 times B22, and then I have A21 times A22 times B22. So this guy gets completely canceled, and then I cancel also those two. So this product is done apart from the term that remained. And now here we have A21 plus A22 times B12 minus B11, which is exactly like canceling this one, right? Because those two are multiplying by the negative of this. Okay, so this is exactly our C12. Okay, so I guess the decomposition that we could have done, if you want to see this like in a simpler manner, is that this will be like, let me just do in hindsight the decomposition, right? So we would have, oops, sorry, what was this here? It's minus S1, right? So this is minus S1. And this A21, A22, this is S1. And this is S1. And well, yeah, we have the like B11 minus B12, right? So then you can see that the SIs all cancel as well. That's what we saw, right? So that's okay. All right, so we know how to compute C12. And, you know, if you just follow like this computation here that I just wrote exactly because it's very confusing to write on the fly, you can compute like C21 and C22. Now, what's the idea? The idea is that, okay, now we used only 7 products, right? We used 7 products and we used a bunch of sums. How many sums did we use, right? So we used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we use these 18 sums and 7 products to compute the matrix, right? So, all right. So the correctness falls from the computations that we just checked, right? We checked for C11 and C12. You can check the other two. All right. So what did we do, right? So to compute AB equals to C in this new way, we use 7 multiplications, which are the PIs. We use 8 additions to compute the SIs and the TIs. And we use 10 more additions to compute the CIJs from the PIs, right? That's what we used. Now, what is a recurrence? A recurrence here is that, well, if we say that MM is the time it takes to multiply 2 matrices of dimension n, this is less or equal than 7 times like our 7 products plus 18 multiplications, right? And this is the time it takes to multiply. Sorry, time it takes to add. Like n by 2 by n by 2 matrices, right? Because that we know is n squared, right? Is n over 2 squared, pretty much, right? So we have 18 of these. So then, you know, you can either use the master's theorem that you learn, or you can just do this recurrence. Like this is such a simple recurrence, you can just do it on the fly, right? That if we know that n is equal to like 2 to the k. So if we say like mm like 2 to the k, it will be less than or equal than 7 times mm 2 to the k minus 1 plus 18 times c times 2 to the 2k minus 1, right? And then if we unravel this recurrence, what do we get? Like this is less than or equal than 7 to the k times mm of 0, right? Which is a constant pretty much, right? And then we have plus 18 times c times, well, yeah, so here, what are we going to have? The first thing that we had was we start with 2 to the 2k minus 1. And then we're going to be, we're going to have 7 times 2 to the 2k minus 2 plus all the way up to 7 to the k times 2 to the 2, sorry, 7 to the k minus 1, 2 to the 2, 0, like k minus, right? Like k minus, well, that would be like 2 to the 0 times 1. Correct? Because every time now, if I would just want to unravel each of these recurrences here, I have 7 times the cost of the addition. Does that make sense? Okay, and then once you do this, right? So what do we have? What we have here is that, all right, well, so this is essentially, right? So if we look at this, this is going to be big O of 2, sorry, so it'd be big O of 7 to the k, but then this is exactly, right? So this is big O of 7 to the k, but what is big O of 7 to the k? Well, if n is equal to 2 to the k, this is exactly O of n to the log 7 base 2, right? So, all right. So now, what do we do this, right? So based on the recurrence that we got, right? So we got that this is O of 7 to the k. And now this is O of n to the log 7, but log 7 base 2 is 2.807, right? So this is already a huge improvement from n cubed, right? So this is much better asymptotically, much better asymptotically than n cubed, right? Just by reducing the number of multiplications, right? So, all right. And now, all right, so then the question became, right? So, okay, so now we know that the time it takes to multiply two matrices is somewhere between n squared and n cubed, but it's definitely not n cubed, right? Like it's upper bounded by this like n to the 2.807. Now, so then what we can define, since matrix multiplication is such an important problem, right? Like is probably the most or the top 3 most used algorithms in life. Okay, like is one of those, right? Like, and so we want to really learn what is the complexity of matrix multiplication, right? So if we define omega or omega multiplication as the matrix multiplication exponent, we want to know if omega is between 2 and 3. But what is this definition? How do we define this omega, this matrix multiplication exponent? Well, here's how we can define it, right? Suppose we have an algorithm, okay, for n by n matrix multiplication that has running time O of n to the alpha. Then we're saying that omega is less than or equal to alpha, right? So omega here, the idea, so what is the kind of intuition for defining omega, right? Like omega is the exponent of like the best algorithm. That's what we want to capture, right? Like of the best algorithm for matrix multiplication. And to define it, right? So the idea is that if any algorithm that can solve matrix multiplication has running time O of n to the alpha, then omega is less than or equal to alpha, right? And for any epsilon bigger than 0, there is an algorithm for n by n matrix multiplication running in time O of n to the omega plus epsilon. Does that make sense? So that's kind of the intrinsic exponent for matrix multiplication, right? Because it may not be the case that there is one algorithm which achieves this omega, but what we want is like, if you take omega and you add any constant epsilon, there will be an algorithm that has exactly that running time. Does that make sense? So that's how we formally define this omega, okay? Like the matrix multiplication exponent. Okay, cool. Okay, so, and as we'll see today, right, like omega, this omega, which is the omega for matrix multiplication, is so fundamental that we even drop the subscript multiplication. We just say, whenever we say omega, you know we're referring to omega for matrix multiplication, right? So this is a fundamental constant in computer science. All right, so what is currently known? Well, what is currently known is that omega is between 2 and 2.376. And I think maybe in the previous months, this was improved to something better. Okay, so like, I think this is outdated. I forgot to update. So like this may be better today. Like today, it was improved this year again, right? And the open question here is, what is the right value of omega? Is omega equal to 2? Okay, or is there like a limit? Okay. So, all right. And what does it mean for omega to be 2, right? If omega is 2, it's kind of really impressive that the time it takes to multiply two matrices is like asymptotically the same as the time it takes to add two matrices. And those operations are very different, right? Like certainly one is much easier, like it seems much easier to us than the other, right? So, all right. Okay, so now let's talk a little bit about historical remarks, right? So Strassen's work is not only important because it gives us a fast algorithm for matrix multiplication, and is a fast and quite simple, right? It's a very practical algorithm to code, but it's also important because it startled the community back then that the trivial cubic algorithm could be improved. This was a belief that people had that, oh, this is the best we can do, right? But then when Strassen came up with this, it's like, wow, okay, this is really impressive. And it really started all this research kind of direction, right? And it motivated work to find better algorithms for all the other linear algebraic problems. That's also a historical significance, right? That people say, oh, looks like this matrix multiplication cannot be improved. And, you know, many other algorithms in linear algebra seemed so easy and natural that they thought, oh, these are the best algorithms. And once Strassen came up with it, like it shook up all of everyone's beliefs and like, well, okay, let's look for better algorithms for all procedures in linear algebra now, right? Like for all linear algebraic problems. So this is pretty cool. Okay, and also in the approach to prove that, to find better algorithms and even more general algorithms that could improve on Strassen's algorithm, right? So this introduced like the complexity of computation of bilinear functions, because the multiplication of two matrices is bilinear in each, is linear in each matrix, right? So you can generalize this to computing bilinear functions, and also to the study of complexity of tensor decompositions. And if you look in today's like machine learning and many other applications, tensor decompositions, even in quantum information theory, like tensor decompositions are very important, and they show up quite naturally in many other problems that we're interested in, right? So, and the study of these tensor decompositions goes back to Strassen and the attempt to find better matrix multiplication algorithms. Okay, so this is quite an important result to know. All right, so now let's talk about how this matrix multiplication exponent appears in linear algebra. But before that, do you have any questions?